Okay, Lab 11, we've come a long way. Faraday and Lenz's laws, and not easy, but I think easier than Biot-Savart and Ampere. So a few words about the lab. The lab is for your learning purposes, both to apply and strengthen our understanding of Faraday and Lenz's law, and give it some real physical situations, at least as real as we can be when we're in remote learning. So my recommendation is try and do the lab exercises on your own and then watch the video. But you can figure that out. You may want to watch the video first, but I think it's better just to do as much as you can and then watch the video. So you read through the description carefully and then you run the video. Now when I run the video, it's going to be a little bit jumpy in this format, but when you run it, you'll see it much more smoothly. So let's see if it goes. So there it is. Five seconds, and that's what happens. It happens so quickly it's really hard to see. So you go back and run it a few times and you'll see that what you'll see is that it starts out white, so there's no magnetic field, and then if we step through it with the stepping button, you see as we start it, the left side is blue, so that means we went from no field to a field into the page on the right side, on the left side, and on the right side it's beginning to become red. You can't tell that yet, but the dots are coming out at us. So on the right side the field is is increasing toward us, whereas on the left side, so that's a change in field, right? If we go back to the original and then we step this side, that is a change in field, even though there was no field. And so Faraday's law tells us, right, that we get a change in EMF whenever we have a change in flux. It's important to remember that. And a change in flux means either a change in field, area, or direction. So in this case, the area of every loop is the same, and the direction of the field switches, but since it's all in one direction, we can think of that as a change from positive to negative. So what's changing in this case is the field. And as long as the field is changing, there will be an induced EMF. And so this exercise is a practice in Lenz's law. This is Faraday's law telling us that we're going to get an EMF, but what's the direction of the EMF? That's what you got to figure out. So if we look at loop A, and we see that the field went from, if I go back to the simulation, and I run it backwards, there's nothing. So in loop A, I'm going to go twice. You see it's getting darker and darker. So the field into the screen is increasing. So what does that mean? That means that the induced EMF and the induced current has to oppose the change. And remember, it's opposing the change in flux. It's not opposing the field, it's not opposing the flux, it's opposing the change in flux. There's where you're going to get confused. And so the induced current, since the field into the page is increasing, little x's or plus signs are increasing, we need to generate a counterclockwise. The EMF is going to generate a counterclockwise current, which is going to tend to oppose the change in flux, right? So the other way of thinking of it was maintain the original. If we go back to the original, well, it's not going back. But anyway, we started with 0. So another way of thinking of it is we want to keep it at zeros. So if we're getting flux into the page, the induced EMF needs to produce flux out of the page, tending to keep the thing at 0. So there's lots of ways of thinking about Lenz's law. So that means that on the left-hand loop, the induced EMF and the induced current is going to be that way. What am I doing? I'm using right-hand rule number 3. I'm curling my fingers in the direction of that arrow, and my thumb is pointing out of the screen. And so the field and the flux are going to oppose the increase in flux into the screen. And by the same argument, since loop C on the right-hand side has field coming out of the screen increasing, in order to keep it at 0, in order to maintain that increase in flux coming out of the screen, you're going to have a clockwise EMF and a clockwise current, which will produce a current and a field and a flux going into the page. And of course, since the loop B is seeing an increase, half of it increasing one way and half of it increasing in the opposite direction, those are going to cancel out and there'll be no induced EMF in loop B. And as we continue to increase, let's see if I can get back to that. As we continue to increase, that's going to continue, right, getting stronger and stronger. So we're getting the same thing. The field on loop A, for example, is getting stronger and stronger into the page. So we're going to continue to oppose that increase. And then we reach a point where it seems to be constant. It's not changing much. And now it's decreasing. So the field, I'm looking at loop A, right? The field into the screen, the blue field, is getting less. You know, we went from a strong field to we're going towards a weaker field. And so now we're going to try to oppose that change, that loss of flux. We're losing flux. So in order to oppose the loss of flux, now we have to induce an EMF and a current in this direction, which will, so now we're opposing the change in flux, right? But we're actually in the same direction. The field and the flux is in the same direction of the flux that we have because it's decreasing. So we're going to want to increase it. And so at that point, when it goes from its maximum blue value to now decreasing, the direction of the induced EMF and the current is going to shift. And similarly for loop C in the opposite direction, right? And loop B is just going to be throughout equal and opposite in each half. And so the net change in flux through loop B is always going to be 0. And then if we continue to step this, if this will keep running for me, getting lighter and lighter and lighter and lighter. So we're continuing to lose flux on loop A into the page. So we'll continue to have a clockwise current opposing that decrease in flux into the page, trying to maintain the flux until we get back to 0, and then it switches to the other side. So now on loop A, we have an increasing flux out of the page, right? It's now getting red. And so since that's increasing, we're going to oppose that by getting a field in the opposite direction. In other words, if we step back to where, if this doesn't want to go backwards. But anyway, if we step back to 0, now it's getting redder and redder. That's a field coming out of the page. So to oppose that, we need a field and a flux into the page, and that's the same direction, right? When you use Lenz's law, you want the field to be into the page. This is a lot of words. I hope you can follow it. So I'm pointing my thumb into the page because that has to oppose that increase of red coming out of the page, and that gives me the same thing that I had. That gives me a clockwise induced EMF this way. So just to summarize, when the field goes from blue through 0 to red, the direction of the induced EMF doesn't change. It's when the field goes from maximum blue and starts decreasing, or from maximum red on the other side and starts decreasing, that's when the flux changes direction. Okay, that's a somewhat long-winded explanation of this, but you're free to be selective, watch part of it, not watch part of it. In the end, you've got to figure this out. You've got to work this out in your own mind as to how you come up with the answers. But that's my way of thinking about it. And I'll repeat it one more time. Lenz's law says that you oppose the change in flux. So keep in mind, you don't oppose the field, you don't oppose the flux, you oppose the change in flux. And what that means, and you can see it here, is sometimes you oppose the flux in the field and sometimes you support the flux in the field. So when it's increasing, you're going to oppose the flux in the field, because that's the change in flux is in. But when the flux is decreasing, you're going to actually induce an EMF and a current that's going to be in the direction of the field and flux because it's decreasing, and you're going to try and prevent the decrease. So keep that in mind. And all you're doing in this question is identifying the direction of the current, and the direction of the current, keep in mind, is in the direction of the induced EMF. So good luck with that. And one last thing, just in case you're interested, because I like to think, when I see these simulations, I like to think like, okay, what kind of real situation would create this? And so here's a loop in a magnetic field, and in this case the loop spins. So a spinning loop in a magnetic field would undergo a change like this, right? So if you imagine the loop where the plane of the loop is perpendicular to the field, or the direction of the loop is in the direction of the field, then there would be a maximum flux through the loop. As the loop rotated 90 degrees, there would be no flux through the loop. Then as it went another 90 degrees, there would be a maximum flux in the opposite direction through that loop. And then 90 degrees would put it back to 0. And so it would go through this same cycle as this loop spun. It would have the same effect. And so you do, when this spins, get an alternating EMF that goes back and forth from one direction to another when the field goes from maximum increasing to maximum decreasing on both sides. The other way of getting exactly this situation would be to put the loop so that the plane is perpendicular to the field, or the loop is facing in the direction of the field. No, actually, since this starts at 0, yeah, anyway, so put the loop so that it has a maximum flux through it, and then make these magnets electromagnets like coils so that we can turn the field off and on by controlling the coil. And so the loop wouldn't rotate, but the field, the magnets being electromagnets, could be increased and decreased by, if you imagine an electromagnet that's where the field is controlled by current through a coil. I couldn't find a picture of that. And if it were magnets like this, you would have to have side by side two magnets of opposite polarity. Actually creating this very situation would probably be technically difficult, where the field from one side to the other had a very sharp edge like that. Okay, ready to move on to the next one. Okay, question number 2, simulation number 2. Actually, it looks like the last one, right? Only in this case, the field is constant. And the loop moves. So look at that and think about what you're going to get. Changing flux. So try and do this one on your own. Don't do as much as you can. Do it and then come back and check and see what I say about it. Okay, you're back. You've done it. So notice as it moves through the blue, it's moving, but there's no change in field, right? So once again, let me just write this down. So there we have Faraday's law, minus n d phi dt. But the n in this case is 1, so I take it out. And so we have d phi is ba cosine theta. So the cosine theta isn't changing. Well, it shifts 180 degrees here, but we account for that by a plus or minus sign. The b stays constant, but the a changes. But it's the a exposed to a changing field, right? Something has to be changing. So the flux through this loop, the whole time it's in the blue region, there's no change. It has flux, but it's constant. It's only at the interface, when it's moving through the transition region, that there's any change. And then once it goes through the red region, the flux will go to its opposite maximum value and be constant. So it's only during that transition time that we get an induced EMF. And from this, since the B is constant and the L is the length of the loop, right? And so that's constant, but the width of the loop in the field, and so we've derived this earlier, but it's the dw dt, which is the velocity. And so, oh, it's not on the screen, but it's BLV, right? That's the equation we use. E equals BLV is what we need to use. And so the L you need to measure. There's a little bit of uncertainty there. It's around 3.3, I think. But you may get something different by plus or minus 0.1, but that's what I got. And then the, no, that's not the L. That's the L, about 3.3. And then the width is also about 3.3. Again, there's a little bit of uncertainty there. 3.3. And the B is given. This is negative 0.5. And this is positive coming out 0.5. And the velocity you need to measure. And I think you can round it off. It actually measures pretty easily. And good experimental practice would be to measure it over a couple intervals. Let's just do that. Let me show you what I did. So I'm going to reset it and then click it one step, and it clicks 1/10 of a second. And if you use your cursor to measure the position at the beginning and the end, you'll see how much it changes, and then I can click it another step and measure that, and click it another step and measure that, and see if it goes the same amount each time. And then you could go back to the beginning and run it for 1 second, and then measure that distance and see how it goes. And then if you wanted to check at the other end, or actually another good check would be to run it the whole time, get the whole distance in time. And I think you'll pretty much get the same answer for all of that. And if I tend to use the more rounded number if there's any doubt. Okay, so you have so there's not going to be any change, but notice here, this is where you may mess up. When it gets to the edge, now it moves in, and it's not moving from a field into no field, so it's losing blue and gaining red. So the change in field is actually the final minus the initial. And so the change in field as it moves through is going to be the 0.5 minus a negative 0.5. So the change in field is actually 1 Tesla. And you can compare that to the next one to see that if you move from a field into no field, then you would use the 0.5 Tesla. But since you're moving from a field into a field in the opposite direction, the change in field is actually 1 Tesla, not a half a Tesla. And that's what you need to use here. So let's go to the next one. Whoops, I forgot, Lenz's law. So you're losing flux into the page, right? You're losing this, so you're going to try and replace that flux that you're losing on the one side. And so the flux that you're losing, if you try and replace it using right-hand rule number 3, would be a current in this direction. And here you're gaining flux on the right-hand end. So you want to induce a current and a field to oppose that increase. Oh good, that's in the same direction, right, using right hand. In both cases, you want the current to circulate clockwise, which leads the EMF to be clockwise, which leads to a current which is clockwise, which leads to a field into the screen, which supports the loss of blue and opposes the gain of red. I hope that all makes sense. Lenz's law. Okay, here we are, number 3. If we run it, you're pulling a loop, and it's moving from a field into no field, so there's a changing flux throughout that, right? Because there's no period where it's moving where the flux isn't changing. And so this is another, like the last one, it's BLV, but now you don't have 2 opposing fields, you only have a single field, single constant field. And you can think of it, when you're thinking of BL, of flux, there's actually 2 ways of thinking about this. Oh, by the way, do this first, right? Do the thing, do it as much as you can. You could submit your answers or not submit your answers, but do as much as you can before you listen to my explanation. It'll be a much better learning experience for you. So remember, the BLV, which we're going to use, comes from, the change in BA cosine theta over time. And again, cosine theta is usually when the coil is spinning or the field is changing direction relative to the coil. That's not happening. And strictly speaking, is the A changing or the B changing? Well, I think of it as the A changing. And you say, but the A isn't changing. But the A that's in the field is changing, right? So however you want to think of it is that the field is changing or the A is changing. It's the A in the field, and so as you step this, you have less and less A in the field as you step it. Okay, so what do you need? You need the B, that's given. You need the A, you're going to have to measure that. Again, the way I measure is when I put the crosshairs on the line, I center it. I always center it, not measuring edge from edge or inside edge. Put the crosshairs right on the center of the line at each end and get the length and the width, right? Because you need the length, and the width over the time is the velocity. So it's going to move the length, the width. We're calling this the width, and we're calling this the length. It's going to move the width of the loop over the time period shown, and that will give you the velocity. So you want to do those measurements carefully. And then there are the so that gives you the EMF, right? This is, in fact, the EMF. And remember, EMF is induced voltage from this motion. And so the current is just going to be using Ohm's law, V equals IR. It's going to be the V, or the EMF, over the R, and the R is given. And since the rate of change, or the V, the velocity is constant, the area is constant, the field is constant, the rate of change is constant, that's going to be a constantly induced EMF, which gives rise to a constant current. And given that you have a current in a magnetic field, there's going to be a force opposing it. So notice, as the loop moves, there's a constantly induced current, and that current in the red area is in a magnetic field. So figure out what the force is on those wire segments as it moves through the magnetic field. Go ahead and do that and see what you get. So we're losing flux out of the screen. So using right-hand rule number 3 and Lenz's law, you can come up with the fact that the induced EMF and the induced current has to be counterclockwise to replace the out-of-the-screen flux that you're losing. And so there are 4 wire segments. This one is no longer in the field, so it's not subject to a force. The upper segment is at least partially in the field, and so if you use right-hand rule number 1, where the field is out of the page, you go L cross B gives you a force on the upper segment, which is up. Similarly, when you do the lower segment, you'll see the force is down. And when you do the side segment, you'll see the force is this way. And so the force on that wire in the magnetic field is opposing the direction you're pulling it. And for that reason, you have to apply, to keep it moving at a constant speed, right, you've got to apply an equal and opposite force with your hand, right? Because if the velocity is constant, the acceleration is 0, and so the sum of the forces in the x direction have to be 0. And so the hand force has to be equal and opposite to this force. And what is the magnitude of that force? The magnitude will be given by the F equals IL cross B, or ILB sine theta. Of course, the sine theta here is 90 degrees. The L you need to measure. You needed that for the BLV, right? And the B we know. And the I we calculated over here, and all that should give you the magnitude of the force. For the hand, it's in the I direction, and for the on the wire, it's in the negative I direction, and they're equal and opposite. Okay, this one should be easy. Watch. The bar slides. You see the induced EMF is constant. The position is given. The time is given. Getting the velocity is easy. And so you have the induced EMF. You can measure L. And remember, measure center to center. So this is a pretty thick line. Make sure you put your cursor on the center of the upper bar and the center of the lower bar, because there's a lot of thickness to that bar. So you're always measuring center to center when something has substantial thickness like this does, in order to get the same numbers that I get. And so what you have is you have your induced EMF equals BLV, and so you're looking for B, and so that's just the induced EMF, which is given, divided by the LV, which you need to measure, but it's pretty easy to measure those. And notice that when the bar is sliding this way, the flux is increasing and the deflection is negative. You see the number's negative. So that means the current is coming out of the plus terminal. Usually it reads positive when you put current into the positive terminal of a meter. And so that means that the current is clockwise. And so the current induces a field, using right-hand rule number 3, induces a field and a flux into the page, and since you're going to oppose the increase, that means the field must be out of the page, and if you look at it, you'll see a bunch of dots here, if you look carefully, which indicates it's out of the page, so that's the direction of the field. And so you should be good on this one. Okay, as usual, play the simulation, watch it, see what happens. So there's a lot to watch, right? It's graphing it as it changes. The field is changing, the flux is changing, and there's an EMF. And it's a constant output until it reaches some maximum or minimum value, and then it changes direction. So see if you can make sense of that. Just look at that for a while and try to make sense of it, and then go to the questions and answer as many of the questions as you can, and then come back and see what I have to say about it. Okay, let's see if we can use the slow stepping function. Keep in mind, this is all happening to a wire loop that's facing the direction of the field, either positive or negative. All we see is a line, but it's actually a circular loop on its side. And so the field, there's a changing flux through the loop, and so the loop is going to have an induced EMF minus n d phi dt, right? But the n is 1 because it's just a single loop. And the phi, the phi, is BA cosine theta. And the angle's not changing, nothing's twisting, so the cosine of theta is constant. The area of the coil is going to be pi r squared. You have to measure the diameter and get the radius. That's the area of the coil, pi r squared. And so it's the B that's changing. So when we take the derivative of the flux, all we're doing is we're taking the derivative of B with respect to time. And since it's constant, it has a constant positive value here and a constant equal negative value there. All we need to do is get delta B, delta T. And since the derivative is a constant value through this part of the cycle, constant positive value, then it goes at this point to a constant negative value, and then at this point it goes back to a constant positive value, And it would continue forming what is called a square wave. So this we would call a triangular wave because it looks like triangles. And the output is a square wave. And you'll see this if you've done the assignment. You saw this in the next to last problem in the assignment. So in terms of this triangular wave, remember it's centered at 0. And so it has a positive and negative value. That's called the amplitude, not this distance, but the distance that it rises above 0 and goes below 0. So that plus or minus 5, whatever it is, you'll have to read that, is the amplitude. And the period is one full cycle. So if you start here, you have to go to here to get the period. This is only half the cycle, right? This is the positive and negative part. That's a full cycle. So that's the period. Or you could get the period measuring from here, where it's rising positive, to here, where it's rising positive. That should give you the same length of time, which would be the period of the waveform or the period of oscillation. And the frequency is 1 over the period, so, and vice versa. If the period is 1/10 of a second, the frequency is 10 times per second. Or if the frequency is 1,000 times per second, the period is 1/1000th of a second. That's how that works. And in order to get the EMF output, as I mentioned, you do need to know the area, and you need to know the dB or delta B, delta T. And so just measure the minimum value, the maximum value, that's your delta B, measure the time of half the period, divide those, and you'll get this value. And use your cursor, remember center to center, get the diameter, divide by 2, get the radius, multiply by 5, that will give you the area. And then in terms of the direction, if the field in this direction, when it's increasing in this direction, then the induced EMF has to produce a flux which opposes the increase. And so that would mean that the current needs to go in here and come out here. That's when the field in the the positive direction is increasing, right? And if it were decreasing, then, like, I'm not sure where we're at, but if this were in a time when the field were decreasing in this direction, then the current would have to go in here, using right-hand rule number 3, come out here, because my thumb would have to point in the direction of the field. Because it's decreasing, the induced EMF is going to try and prevent the decrease. Again, Lenz's law. Okay, as usual, play the simulation, look at it, think about it. Before you even look at the questions, just see if you can understand. So what do we have? So we have a loop, a wire loop, spinning in a constant magnetic field. It's rotating around an axis. So notice the blue line's going in one direction, the field is constant, and it oscillates back and forth. And so the flux through the loop changes, producing a sinusoidal induced EMF output. So how does that make sense? Can we make sense of that? If we pause it and step it, so when the coil is like this, if you can picture it, there's no flux going through the coil. But notice the EMF, interestingly enough, the EMF is at a maximum value. It happens to be a negative value. And that's because although the flux through the loop at this point is 0, it's changing most rapidly, right? Because the EMF is the change in flux. So as I step this, well, I wasn't quite at the maximum. Yep, see, it's still going down. Now I'm at the maximum value. It's 0. And if I keep stepping it, now the thing is swinging back. You got to picture this in 3 dimensions, right? So now the flux went from 0. It's increasing. It's increasing, and it's going to reach its maximum value here. So here's a maximum value, but even though the flux is at a maximum value, notice the M output is 0. And we've seen that before. And now as we step it this way, it's going away from a maximum value. And so where the flux is at its maximum value, the rate at which it's changing, that's a little bit tricky. You need to think about that. When the flux is at its maximum value, the rate at which it's changing through the loop, it actually reaches 0 for an instant and is at a minimum value. And if we keep going, then the whole thing reverses. And so how do we understand this? Well, we use Faraday's law, as usual. And the n is 1, and then we're going to go do dBA cosine theta dt. And notice the b is constant. Those are the arrows in one direction. The a is constant, actually. It's the theta that's changing. So when we do d theta dt, that's the change in angle with the change in time. That's actually what we learned last semester as omega. It's the rate at which the flux is changing is the angular velocity at which the coil is spinning. Wow, that's a lot. But it really pulls in what we learned last semester. Think about this. This coil is spinning with a constant rotational velocity, and that's what omega is. And remember, delta theta delta t was omega average from last semester, and the d theta dt is omega. And omega is a constant value. So how do you get the constant value? Well, you just take 2 pi radians, the one complete rotation, and divide it by the period. And so there's the period, right? That's the period, or you could get the period here. It's the time of one complete cycle. Or you could get the period from falling through 0 to when it falls through 0 again. Any of those two things should give you the same period, and if you divide 2 pi by the period, you get the angular frequency or the angular velocity of the coil as it spins. And as we discussed previously, 1 over the period is the frequency. So don't get confused between the frequency, which is cycles per second, right? The period is seconds per cycle, and the frequency is cycles per second. We discussed that earlier. Whereas the angular frequency is radians per second. How many radians it goes in 1 second as opposed to how many cycles it goes in 1 second. So they are related by 2 pi, and it's easy to get them confused. And once we know the period, we can get the frequency by taking 1 over the period, or we can get the angular frequency or the rotational rate of the coil by taking 2 pi and dividing by the period. And then we also, the amplitude of the wave, remember, is always measured from the center to the peak and the trough, and it goes above and below 0 by the same amount. And so if this looks like it's a little less than 2, if this were 2 millivolts, it would be plus or minus 2 millivolts. Okay, this can be a little challenging. Let me help you with the measurements and the calculation. So to get the maximum value, I think the best thing is to step this thing up till it gets to, let me pause the video, it's taking too long, but anyway, get it up to the maximum value where you can measure it with your cursor here. And it's easier to do it when it's not all compressed in several cycles. And then run it down to the other side where it crosses, and that would be half the period, right? And then you can run it out to where it comes back, and that would be the full period. And it doesn't cross exactly, so you're going to have to measure that. Anyway, just for your reference, you should get something around 1.6 for this, maybe plus or minus a little bit. And this is a little bit more than a half a second, 1.5 something. So I got 350. I used 315 for the period. And so when you go to get omega, which you'll need, you just take 2 pi and divide it by whatever time you used. I used 315, and that'll give you the radians per second. And so the maximum value is plus or minus something around 1.6. That's millivolts, of course. And while I have the screen here, I want to show. So then we need to calculate the field, right? So we're using that the EMF equals minus n, which is 1 here, dBA cosine theta by dt. That's 1. So I'm going to the whiteboard to help you with this calculation. So we have Faraday's law, E equals minus n d phi dt. And n is 1, it's just one loop. And so E is dBA. Phi is BA cosine theta, right, by dt. But the B is constant, the field is constant, and the area of the loop is constant. You need to measure that. I'll show you how in a minute. And so we have that E equals constant B, the constant A, by the derivative. That's the thing that's changing, is theta. But we need to differentiate that by dt, so we need to change the theta, the variable theta, to the variable t. And the way we do that is omega equals delta theta over delta t, or d theta dt. So d theta equals omega dt, or what we'll use here is that theta equals omega times the time. If you take the angular speed and multiply it by the time, you get the angle through which it turns. And so now we can rewrite this as BA d cosine omega t by dt. And then when we take the derivative of that, we get that E equals BA sine of cosine omega t dt times the derivative of that argument. So the omega, the derivative of omega dt by dt is omega. And then we're left with the sine of omega t. And there's a negative sign here, but we don't need to worry about that. And so the field, the EMF and the field are varying together, but what we want is the maximum value. We want that and so this expression gives us what we see in the graph, that the EMF varies according to the sine of omega t. And so if we take the sine, when the sine is 1, when it reaches its maximum value, then we can say that E max equals, that's BA omega. And so to find B, You just take the maximum value of the EMF, which you measure from the graph, and you divide it by the area of the loop in meters per second squared. This is going to be in millivolts, and so you'll get your answer in millitesla times omega. And we already said what omega was. Omega is 2 pi over the period, which was about 3.15 seconds. And the area you got to measure. So you're going to have to go back and measure that. And the Emax, we talked about that. And so let's go back and get the area and also try and puzzle out the direction that the coil is spinning. Those are the last two things that we need to look at. So to get the area, you want to move the loop so that you're at the maximum EMF when the coil is facing us and parallel to the field, and the flux through it is 0. So notice from the green arrow that the current is going around this loop clockwise, and if you use right hand rule number 3, you'll see that your thumb comes out of the page. So if you take this loop and you rotate it clockwise, looking at it from above, if you rotate it clockwise, your thumb is going to start pointing in the direction of the field, which means that as the field increases, the current is going to, the induced current is going to add to it. On the other hand, if this comes out of the page this way, but if that side is going into the page as you go forward, then your thumb is going to turn in the opposite direction of the field and oppose the increase in flux. And so that's what it should do. So if you think about this, you should be able to come up to the conclusion that as we rotate it, this side, as it gets smaller, is rotating backwards into the page, while this side is rotating out of the page. And looking at it from above, that would be a counterclockwise rotation. It's a very tricky three-dimensional visualization challenge. Okay, I think we've covered everything.